Every year, the world produces over 4 million tons of hollow structural sections, and that's just in the US. Picture this, that's enough to build 400 Eiffel Towers annually. But behind these massive numbers lies the silence of steel giants we never see, because they're hidden inside buildings, bridges, and machines. How does rusty scrap metal transform into tubes capable of supporting the weight of entire bridges and weathering the storms of time? And what secret makes them both lightweight and incredibly strong? Stick around till the end, and you'll discover a secret you never knew existed. The market for hollow structural sections, where our heavy wall tubing reigns supreme, is a massive chunk of America's steel industry. Every year, the country cranks out over 4 million tons of these tubes. That number is mind-blowing. To put it in perspective, the entire Eiffel Tower weighs about 10,000 tons of steel. That means in a single year, American mills produce enough square and rectangular tubing to build 400 Eiffel Towers. It's an entire forest of steel giants sprouting up annually. We just don't see it because it's hidden inside structures. Mountains of scrap metal, remnants of cars, construction frames, old machinery sit waiting for their fiery rebirth. A giant crane with an electromagnet scoops up this metallic chunk and feeds it into an electric arc furnace. Down there, in that roaring inferno where temperatures hit nearly 3,000 degrees Fahrenheit, this scrap metal transforms into a boiling, blinding lake of molten steel. Into this melt, like a chef adding spices, they introduce alloying elements, so the future pipe isn't just strong, it can withstand extreme loads and won't crack in freezing cold. Then this river of fire flows into a continuous casting machine, where it cools and solidifies, becoming long, massive steel billets. For our future pipe, these are typically thick, round slugs called blooms. Automatic cutters slice off pieces to the required length, and these hot but now solid cylinders are ready for the really interesting part. This is our blank, our solid chunk of metallic dough. But how do you make a hole in it when it's hard as rock? To do this, it's sent to a heating furnace where its temperature is brought back up to that perfect plastic state, 2,300 degrees Fahrenheit. And from there, glowing white hot with a blinding yellow radiance, it moves to the piercing mill. This is the heart of the entire process, and it's real industrial magic. Picture two massive barrel-like rolls spinning in the same direction. They're set at an angle to each other. The hot steel cylinder enters between them, and here's where something incredible happens. As they spin, the rolls don't just forcefully push the cylinder forward, they also make it rotate at a crazy speed. Because of this rotation and compression, enormous stresses build up right at the center of the metal cylinder. And the metal there literally loosens up, preparing to split. And at that exact moment, from the other side, a special piercing rod, or mandrel, is fed in to meet it. It plunges into that loosened center like a knife through butter, literally punching straight through the solid billet, transforming it into a thick walled tube. It's an incredible sight. A solid chunk of metal becomes hollow in mere seconds, all happening with a roar and grinding that shakes the ground. The piercing process was invented in the late 19th century by the Mannesmann brothers in Germany and remains the primary method for producing seamless tubes to this day. But now we've got a round tube, and we need a square one. Our hot, freshly pierced tube immediately moves to the next stage, the forming mill. This is a series of roller pairs, but these ones aren't round. They have special grooves whose shape gradually transitions from round to square. The tube flies into the first pair of rollers, which squeeze it slightly from the sides. Then it rotates 90 degrees and enters the next pair, which squeezes it from different sides. And so, step by step, passing through several of these gates, our round tube transforms right before your eyes into a perfectly square one. It's like a skilled sculptor, gradually, blow by blow, giving stone its desired shape. The final finishing rolls calibrate the tube with incredible precision, guaranteeing that all its walls have uniform thickness and all corners are perfectly square. The standard sizes are impressive. There are tubes with cross-sections of 500 by 500 millimeters. That's about 20 inches wide. And the wall thickness on these monsters can easily exceed 25 millimeters. Picture a steel wall as thick as a big encyclopedia. The weight of such a tube is simply colossal. A single yard of this pipe can weigh over 800 pounds. That's like having 4 grown men standing on every yard of its length. And a standard 40-foot section? That'll clock in at over 10,000 pounds, the weight of 2 full-size SUVs, like a Range Rover. And that's just one piece. But here's the thing. Their real genius isn't the weight itself, but how intelligently it's distributed. That's their superpower. Picture a solid steel bar and a hollow pipe of the same weight. The pipe will be way more resistant to bending and twisting. Why? Because all the material sits on the outside, as far from the center as possible, and that's exactly where the greatest stresses hit under load. The hollow core? It just saves weight. Same principle as bird bones, hollow but incredibly strong.
That's why hollow profiles have the highest strength-to-weight ratio of any structural steel shape. This makes them the perfect choice when you need maximum rigidity without extra tons, in crane booms, heavy equipment frames, bridge trusses, and even roller coaster structures. It's because of these tubes that modern skyscrapers can withstand hurricane-force winds, and bridge structures last for decades, carrying millions of tons of cargo. From the final roller, a long, red-hot, now square tube emerges. It travels along a roller conveyor to a cooling table, where it slowly cools down, gaining its final, rock-solid strength. During cooling, the metal can warp slightly, so each tube is run through a straightening machine, a system of rollers that straightens it to perfectly linear precision.
Now we've got a perfect, strong, but really long pipe. Time for the final operations. A massive saw roars to life and cuts it into standard lengths, say 20 or 40 feet. Each section goes through strict quality control. Specialists check its geometry, wall thickness, angle precision. Then they X-ray it with ultrasound to make sure there aren't any hidden internal defects. Modern flaw detectors can spot microcracks smaller than a millimeter, invisible to the naked eye. Only then does the pipe get marked with all its info: steel grade, dimensions, batch number, production date. The finished, inspected pipes get bundled by robotic cranes, strapped down with heavy steel bands, and shipped off to the warehouse. And just like that, traveling from rusty scrap metal through the fiery heart of the furnace, surviving brutal piercing and precise forming, this humble yet incredibly strong steel rectangle emerges, ready to become the silent but reliable backbone for humanity's most ambitious creations. From the skyscrapers of Dubai to the bridges of San Francisco, from oil rigs in the North Sea to the frameworks of space launch pads, everywhere these unsung heroes of modern civilization are hard at work. They don't demand applause, they don't seek recognition, but it's on their steel shoulders that our world stands. And now you know their story, from fire to structure, from the chaos of scrap metal to the mathematical precision of engineering calculations. This is the real magic of industry.
Every year, millions of components, tons of alloys, and hours of high-precision calculations come together in one deadly symphony. This missile isn't simply metal. It's a moving brain, an engine, and coded death that flies over 1,000 miles whilst hiding from radars. How is a secret capable of changing the course of battle born from hundreds of metal sections? Stay until the end. I'll reveal one production secret that few people know. Want to know what's hidden inside? Imagine lasers, press forming, robots welding components in clean rooms with tolerances of 1/100th of a millimeter. All of this for a single flight.
Designing the Tomahawk missile is a symphony of formulae and calculations. Engineers don't simply draw a body. They solve equations that must allow it to cut through air with centimeter precision. Every surface and curve is calculated in computer-aided design systems and undergoes aerodynamic modeling. The goal is to create a body that will fly over 1,000 miles, remaining almost invisible and stable at an altitude of 100 feet or 160 feet above ground. In digital simulations, they test wind force, resistance at speeds of 550 miles per hour, and the effects of rain. One mistake, and instead of a precise strike, the missile will hit a barn on the outskirts. Body components, electronics, payload, all of this fits into nearly 20 feet of length and 20 inches in diameter. It's genuine artistry, packaging death with such elegance. Only after dozens of virtual tests does the missile move to the production phase. After the calculation stage, drawings are transferred to the real world, to factories with high-precision equipment. Here, not a single crack nor an extra micron can be permitted. The missile body, over 18 feet long, is assembled from sections manufactured from high-quality aluminum alloys, sometimes with titanium added. This is an aerodynamically refined cylinder that must withstand overloads, vibration, and temperature fluctuations. Blanks are cut with laser or water jet installations with tolerances up to 1/100th of a millimeter. Then press forming. Large hydraulic machines bend metal like fabric. Welding is conducted in an inert atmosphere, often by robotic arms, to avoid even the smallest oxygen inclusions. Technologists check welds hourly with ultrasound and apply special anti-corrosion coatings. Even the inscription Tomahawk isn't applied as decoration, but as a marker of version and the missile's history. For the cruise missile, a compact Williams F-107 turbofan engine is used, similar to a small aircraft engine, but adapted for high maneuverability. Turbine blades are manufactured from nickel alloys in a form resembling sculpture more than a technical component. They're cast using precision casting methods, then polished to mirror finish to give air minimal resistance. The compressor and combustion chamber are a complex mosaic of dozens of elements. Each component is checked for seal integrity because any micro leak and the missile simply won't launch. The nozzle is manufactured from heat-resistant alloy capable of withstanding flame temperature without deformation. Engine assembly occurs in clean zones similar to laboratories. Workers in sterile suits, stable temperature and humidity. After assembly, each engine undergoes individual ignition testing in a test chamber. The engine simulates genuine flight, but not in the sky, on a concrete table with sensors. Tests last for hours. They check stability of revolutions, temperature, fuel consumption, and even noise, because volume could betray the missile's position. And only when the engine has sung its song is it integrated into the Tomahawk's body, as though breathing life into it. When the body is ready and the engine installed, the missile still isn't ready to fly. It knows nothing yet. It must be taught. Inside is a genuine brain, a node of microprocessors, sensors, antenna, and memory blocks. But the moment it receives its first power signal, a machine consciousness awakens within it. Its navigation is an entire ensemble of systems. Inertial sensors maintain course even if the signal disappears. GPS correction helps prevent deviation from the route. But most important is its ability to see. Special cameras analyze terrain, comparing every hill or bridge with the map stored in memory. If there's forest beneath it when there should be field, it knows something's wrong. It makes decisions. The control system works like nervous tissue, flexible and infallible. Small stabilizers and control surfaces respond to every tilt and altitude change.
And finally, the most important thing, that which transforms the missile from an engineering creation into a weapon, its warhead. It looks simple, a cylinder hidden in the body. But inside is explosive capable of penetrating concrete and destroying equipment. It's manufactured separately, under conditions of absolute sterility. Not a single spark. This is work where mistakes aren't corrected, they're not permitted. Before final assembly, each component undergoes inspection, X-ray, vibration tests, electronic diagnostics, and then assembly. Quietly, step by step, as though someone's assembling not a weapon but an antique clock that must strike just once. And when everything's connected, the missile silently settles into its container. It doesn't glow, doesn't flash, it simply waits. Its flight lies ahead, but it's already ready. 68 million tons. That's exactly how much aluminum humanity consumes in just 1 year. This enormous figure stretches from fizzy drink cans and window frames to the wings of gigantic aircraft. But have you ever wondered how we satisfy such enormous demand without depleting Earth's resources? The answer lies in a revolutionary innovation that's transformed the entire industry: aluminum recycling. Each recycling cycle not only saves up to 95% of the energy required to produce new aluminum, but also allows the metal to be reborn within 60 days, each time retaining its original quality. In this video, you'll witness aluminum's extraordinary journey, from discarded waste to gleaming products that return to everyday life. Unlike many other metals that lose quality with each recycling cycle, aluminum can be used infinitely without losing its original properties. This unique characteristic explains why nearly 75% of all aluminum ever produced is still in use. And the United States has transformed this advantage into industrial might. Thanks to advanced collection and smelting systems, recycled aluminum now comprises over 1/3 of the country's annual supply, saving sufficient energy to power millions of households every year. But the benefits aren't merely economic. Aluminum recycling also plays a critically important environmental role. Each ton of recycled aluminum prevents up to 9 tons of carbon dioxide emissions, representing tens of millions of tons of greenhouse gases that don't enter the atmosphere annually. The recycling journey begins with a step that may seem simple, but ultimately determines the efficiency of the entire subsequent process: collecting aluminum scrap. In the United States, the world leader in aluminum recycling, this system operates on an enormous scale. Every year, tens of millions of tons of aluminum are collected from countless sources, creating a constant stream that feeds the industry. What distinguishes aluminum is its inherent economic value already at the collection stage. A discarded aluminum can is worth many times more than a plastic bottle, giving both individuals and businesses a strong incentive to return aluminum to the production cycle. From collection points across the country, convoys of lorries laden with aluminium scrap steadily roll into enormous sorting yards. Each vehicle is weighed, registered, then its container is tilted to discharge the load onto conveyor belts. Beer cans from supermarkets, food trays from residential areas, and industrial aluminium scrap all converge into towering heaps of shimmering metal resembling silver mountains. Right on site, technicians conduct quick preliminary inspections, promptly rejecting any batches contaminated with excessive impurities or hazardous materials. The atmosphere at the yard is always tense. Thousands of tons of aluminium arrive daily, making this facility the genuine front line of the recycling process. At the recycling facility, streams of aluminum scrap are fed onto long, continuously moving conveyor belts. Optical sensors, acting as electronic eyes, scan thousands of fragments per second, identifying aluminum by its characteristic color and light-reflecting ability. Immediately afterwards, powerful magnets remove any ferrous metals, whilst precisely calculated air jets blow aluminum away from plastic, paper, and lighter rubbish. Through several separation layers, the once chaotic waste mixture gradually transforms into more homogeneous streams of aluminum, neatly collected in gleaming silver heaps. From this point onwards, the aluminum stream becomes chemically homogeneous and strictly controlled, ready to transition deeper into the recycling process. After separation, aluminum scrap is fed into a massive shredding system. Conveyor belts constantly drop beer cans, food trays, and industrial scrap onto counter-rotating steel rollers studded with sharp teeth. With intense crushing force, the metal is instantly destroyed, sending sharp metallic clicks echoing throughout the workshop. In just a few revolutions, hundreds of kilograms of aluminium are drawn inside and shredded into small fragments. A vibrating sieve system controls output size, guaranteeing that all shredded aluminium is reduced to uniform size, creating stable, homogeneous raw material for the next stage. Shredded aluminum fragments are fed directly into industrial furnaces, the heart of the entire recycling process. Depending on scrap type and desired end product, the plant may use reverberatory furnaces, rotary furnaces, or electric arc furnaces. Internal temperature is maintained between 660 and 750 degrees, sufficient to melt aluminum without evaporating valuable alloying components. Aluminum is loaded through an upper hatch or incline chute, then constantly stirred either by mechanical paddles or controlled air injections. Throughout the melting process, thermal sensors and chemical analyzers work continuously, guaranteeing that each batch of molten aluminum meets precise technical specifications. Even after complete melting, aluminum still contains countless hidden impurities invisible to the naked eye. Aluminum oxides, furnace dust, paint residues, and even oils. To eliminate these contaminants, the plant conducts a refining process directly in the furnace. The most common method is fluxing. A special fluxing agent is added to the molten aluminum. Upon reacting, the flux binds with impurities, forming a light floating slag layer on the surface. This layer is then removed, leaving behind purer, refined metal. In more advanced systems, inert gases such as argon or chlorine are injected under low pressure. These microbubbles permeate the molten mass, capturing excess oxygen and hydrogen and carrying them to the surface.
Once molten aluminum reaches the desired purity, it's directed to the casting zone where it begins to take its first clearly defined physical form. This is a crucial transition from liquid to solid, from amorphous metallic mass to structured units that can be measured and transported. Aluminum is poured into molds of steel, graphite, or specialized heat-resistant materials. These may be vertical molds for ingots, horizontal molds for thick slabs, or water-cooled continuous casting systems. Pouring speed, mold temperature, and cooling intensity all are precisely calibrated. If poured too quickly, aluminum may form gas pockets. If the mold is too cold, metal may solidify unevenly. Once aluminum solidifies inside the mold, a hydraulic system carefully pushes out the solid metal. Mechanical clamps grasp the heavy ingot, often weighing dozens of kilograms, lifting it and placing it onto a parallel steel conveyor. The sound of grinding metal echoes throughout the casting shop, whilst the surface of each ingot still glows faintly red from residual heat. One after another, ingots are extracted in rhythm with equipment operation, lining up in neat rows on the moving belt. Sensors quickly scan each piece, checking shape and dimensions. From the casting zone, rows of solid aluminum ingots begin their journey forward, perfectly aligned like metallic bricks, marking completion of a full production cycle. After extraction from molds, aluminum ingots are moved to a preheating furnace to soften them, bringing the metal to ideal condition for rolling. Once the ingot is ready, it passes through a set of counter-rotating steel rollers where enormous pressure flattens and elongates the aluminum block. This process repeats across several rolling mills, with the gap between each pair gradually decreasing. As a result, the ingot, initially several centimeters thick, gradually transforms into a thin, uniform metal sheet. By the final stage, the sheet reaches its target thickness, often to several hundredths of a millimeter, and moves forward as a continuous strip, then is tightly wound into large coils. Amongst countless products made from recycled metal, the aluminum can is the brightest proof of recycling's power, returning to shop shelves in just a few weeks in completely new form. From massive aluminum coils, the can forming process begins with stamping thin sheets into flat circular discs. These discs are fed into a deep drawing press where in one stroke the metal is stretched into a small cup shape. Then the aluminum cup passes through a series of dies, with each stage making the can taller and its walls thinner. Finally, the outer surface is decorated using high-speed rotographer printing, allowing thousands of cans per minute to receive precise labels.